Ettore Majorana was 31 years old, a theoretical physicist holding a brand new chair at the University of Naples, when he walked onto a boat in the dark in March of 1938 and stopped existing. Enrico Fermi, who rationed praise, put him in the same breath as Galileo and Newton. As a boy, he had done impossible calculations under a table where no one could watch him. But the year before he vanished, he published an equation for a particle that is its own antiparticle, a thing identical to its own opposite, with no enemy because it is its own enemy. And then, months later, he withdrew everything in his bank, wrote 2 letters that contradicted each other, and disappeared so completely that 77 years later, the Italian state reopened the file and ruled that he had not died at all. His story runs through Dirac's impossible ocean of electrons, a paper he left buried in a drawer for 4 years, a detector waiting in the dark under a mountain in it, and a photograph taken in a Venezuelan currency exchange in 1955. By the end, you will understand why the reason there is something rather than nothing, the reason you are here instead of empty light, may be the exact property he wrote down before he walked into the sea. So get comfortable, and if you have not already, subscribe or join, because this is the kind of story this channel exists. There is more of it over on the Patreon, where these deeper threads across physics, history, and collapse get the room they need to breathe. Stay with it to the end, because the question of whether the matter in your own body is its own opposite is still sitting unanswered under that mountain, and it is the last thing this video leaves you holding. Let's go back to where there is a particle that does not have an opposite. Hold that in your head for a second, because almost everything you think you understand about matter depends on it being false. Every electron has a positron. Every proton has an antiproton. Matter and antimatter, mirror images, equal and opposite. And when they touch, they destroy each other and leave nothing behind except a flash of light. That is the rule. That is the quiet assumption sitting underneath the periodic table in your imagination, the thing that makes the whole structure feel solid. For every piece of stuff, there is an anti-stuff, and the two are sworn enemies. And there is at least one particle, possibly the most common particle of matter in the entire universe, that may break that rule completely. A particle that is its own antiparticle. A thing identical to its own opposite. Touch it to its own mirror image, and you have not brought together 2 things. You have brought together 1 thing. Twice, it does not have an enemy. It is its own enemy. And nobody can tell you even now whether the most abundant matter particle passing through your body in this exact moment is one of these things or not. The man who first wrote that particle down was 31 years old. His name was Ettore Majorana, and Enrico Fermi, who built the first nuclear reactor and did not throw compliments around, said there were ordinary scientists, and there were good ones who made real discoveries. And then there were the geniuses like Galileo and Newton, and that Majorana was one of those. In 1937, Majorana published the equation for a particle that is its own antiparticle. A few months later, he withdrew everything he had from his bank, boarded a boat in the dark, and performed the same operation on himself. He met his own opposite somewhere off the coast of Sicily, and he annihilated. He vanished into the human equivalent of light. And here is the part that should genuinely stop. 77 years after he disappeared, the Italian state opened the file again, examined a photograph and a witness and a postcard, and officially concluded that he had not died at all. I want to be careful with you, because this is a story where the temptation to exaggerate is enormous, and the real version does not need it. So let me tell you exactly what is established, and exactly what is established is that the equation is real. It was published in a peer-reviewed Italian physics journal called Il Nuovo Cimento, Volume 14, 1937, pages 171 through 184, and the particle it describes now carries his name in every serious physics department on Earth. What is established is that he boarded the boat, that he wrote the letters, that the money is gone, and that no body was ever found. What is established is that in February of 2015, the prosecutor's office in Rome closed its investigation with the formal conclusion that Ettore Majorana was alive and living in Venezuela between roughly 1955 and 1959. What is not established, what has never been established, what 88 years of the most expensive and sophisticated experiments in the history of the field have failed to establish, is whether the particle he predicted actually exists. We have built detectors the size of buildings and buried them under mountains to find out. We have cooled crystals to fractions of a degree above absolute zero. We have waited, literally, for an event that may take longer than the age of the universe to happen even once, and the answer is still not in. That is the thread I want to pull on. 2 disappearances, a man who erased himself, and a particle that refuses to declare what it is. And the disturbing thing, the thing I could not stop thinking about while I read the actual papers and the actual letter, is that they may be the same disappearance. Because if the particle he described is real, then it is the reason there is anything here at all. It is the reason the universe did not annihilate itself into light at the very beginning. It is the reason you exist instead of nothing. The man who is his own antiparticle wrote down the property that may be the only reason matter survives, and then he used that exact property on his own life. You are, possibly, the residue of an imbalance that should not have happened. And the question of whether you are made, at the root, of something that is its own opposite, is sitting right now in a copper-shielded chamber under a mountain in Italy, undecided. We will get there. But to understand why a single equation can carry that much weight, you need to understand the man. And to understand the man, you need to understand what physics looked like the moment he walked into it. Because he walked in at the exact instant the universe was discovered to have a dark twin. He was born on the 5th of August, 1906, in Catania, on the eastern coast of Sicily, in the shadow of Mount Etna. The Majorana family was not ordinary. If you were Sicilian in that era, the name meant something. His grandfather had been a government minister. His uncles were rectors of universities, members of parliament, a finance minister, and one of them, Enrico Majorana, was a working experimental physicist who held a major chair at Bologna and ran the Italian Physical Society for more than 20 years. This was a family that produced the people who ran things. Ettore was the 4th of 5 children, and from the beginning there was something off about how his mind worked, in the way that the word off sometimes means a door has opened that does not open for the rest of us. He was a calculating prodigy. The family stories, and they are documented, describe a small boy who could multiply 3-digit numbers in his head and extract square roots and cube roots without writing anything down, sometimes crawling under a table to do it where nobody could watch him. That detail stayed with me. The instinct, even as a child, to do the impossible thing privately, out of sight, and then come out as if nothing had happened. There is something in that image that runs through the whole rest of his life. The genius performed in hiding, the answer produced where no eye could follow, the refusal to be observed in the act. He was painfully shy. He was prone to dark moods even as a young man. The Jesuits educated him in Rome, in a strict and demanding Catholic environment that left a permanent mark, and the religious devotion it instilled would matter at the very end, when one of the leading explanations for his disappearance involved a monastery. The family moved north when he was about 15. By every account, he was the most gifted of a family already crowded with gifted people, and also the most withdrawn, the one who seemed to live slightly behind a pane of glass that the others could not reach. A household of ministers and rectors and senators produced one son who wanted, more than anything else, not to be seen. They pushed him toward engineering anyway, because that is what you did with a brilliant Majorana boy. Nobody yet understood that the thing he was best at was disappearing. He was supposed to be an engineer. That was the sensible path for a Majorana, and in 1923 he enrolled in engineering at the University of Rome, alongside his older brother and a cluster of other young men who would matter later, including Emilio Segre, who would go on to win a Nobel Prize. And here is where the story turns, not because of anything Majorana did, but because of where he happened to be standing. In 1926, a Sicilian senator named Orso Mario Corbino, who ran the Physics Institute in Rome and also held cabinet positions in the government, did something that almost never happens. He created a chair of theoretical physics out of nothing and handed it to a 25-year-old named Enrico Fermi. Corbino had decided, correctly, that Italian physics was a backwater and that Fermi was the one mind capable of dragging it into the modern age, and then he went hunting for talent to surround him. In the summer of 1927, Corbino stood up in front of a room of engineering students and more or less begged the best of them to abandon engineering and come do physics. Because something was happening in physics that would not happen again. Segre switched. So did Edoardo Amaldi. And the two of them came back, talking about a strange, brilliant, unsociable friend still stuck in the engineering faculty who could do things with numbers that did not seem possible. It took some convincing, but in early 1928, Ettore Majorana walked across to the physics building and met Fermi. What he walked into was not a calm field. Physics in 1928 was on fire. Quantum mechanics had detonated only 2 or 3 years earlier. Heisenberg and Schrödinger had written down their competing versions in 1925 and 1926. And the old comfortable world of solid particles moving along definite paths was gone. But the thing that matters most for our story, the thing that was about to define the rest of Majorana's life, had just happened that same year, in 1928, in the mind of a silent Englishman named Paul Dirac. Dirac had been trying to do something that sounds modest and turned out to be world-breaking. He wanted an equation for the electron that obeyed both quantum mechanics and Einstein's special relativity at the same time. The existing quantum equation, Schrödinger's, did not respect relativity, and Dirac, who had a near-religious faith that the right equation would be mathematically beautiful, kept hunting for one that did. And in 1928, he found it. The Dirac equation. It is carved, in a sense, into the foundation of everything that came after. It described the electron perfectly. It even explained, for free, a property called spin that physicists had only been able to bolt on by hand before. But the equation came with a passenger nobody ordered. When Dirac solved it, the mathematics insisted on twice as many solutions as he wanted. Half of them described the electron with positive energy exactly as expected. The other half described something with negative energy, which made no physical sense at all. Negative energy states should not exist. A particle could slide down into them forever, releasing infinite energy, and the universe would be unstable in the worst possible way. Most physicists would have shrugged, declared the extra solutions a mathematical artifact, and thrown them out. Dirac refused to throw them out, because he believed the equation more than he believed his own intuition, and that refusal is the seed of this entire story. His first attempt to explain the negative energy solutions was strange, and frankly desperate. He proposed that the vacuum, empty space itself, was not empty, He suggested that every single negative energy state in the universe was already full, occupied by an invisible, infinite ocean of electrons, the Dirac Sea. You do not notice it for the same reason a fish does not notice water. It is everywhere and uniform, so it is invisible, and the only way you would ever see it is if you punched a hole in it. Knock one electron out of the negative energy sea, and the hole left behind would behave like a particle with the opposite charge, a positive electron, an anti-electron. This was an absurd idea, an infinite invisible ocean of electrons filling all of space. Even Dirac was not sure what he had. At first he wondered whether the hole might be the proton, because the proton was the only other particle anyone knew about. And he did not want to clutter the universe with a brand new one. The mathematics would not allow it. The hole had to have the same mass as the electron, and the proton is nearly 2,000 times heavier. So the equation was demanding the existence of a particle that had never been seen, with the mass of an electron and the opposite charge, a positive electron. And almost nobody believed it was anything more than a mathematical ghost. And in 1932, it walked into a laboratory. Carl Anderson at Caltech was not even looking for it. He was photographing cosmic rays, the particles that rain down on the Earth from space, inside a device called a cloud chamber, a sealed box of supersaturated vapor where a charged particle leaves a visible trail of tiny droplets, like the contrail of a plane. He put the chamber in a strong magnetic field, because a magnetic field bends the path of a charged particle, and the direction it bends tells you the sign of its charge. He put a lead plate across the middle of the chamber to slow the particles down so he could tell which way they were traveling. And on one photographic plate, he found a track that was clearly a light particle, the mass of an electron, but curving in the wrong direction. It was bending the way a positive charge bends, a particle with the mass of an electron and the opposite charge. The thing Dirac's equation had demanded. Antimatter, predicted by a man who trusted his equation more than his common sense, found by a man who had not been looking for it, in the debris falling out of the sky. Dirac won the Nobel Prize for it in 1933, at 31 years old, the same age Majorana would be when he vanished. The lesson the entire field absorbed, the lesson that hardened into doctrine, was this: every particle has an antiparticle. Matter comes in mirrored pairs. For every electron, a positron. The world is symmetric, and the symmetry is enforced by an equation. And the equation is right, because it predicted a particle nobody had ever seen. That is the world Majorana lived inside, and he was the one person in that world who looked at the Dirac Sea, this triumphant, noble winning idea, and found it ugly. Not wrong, ugly. He thought an infinite ocean of invisible electrons was a clumsy crutch, a piece of mathematical furniture dragged in to hold up a result that should have been able to stand on its own. I want you to understand how alone that put him, because it matters for everything that follows. The Dirac Sea was not some fringe speculation. It was the explanation, the one that had just predicted antimatter and won the Nobel Prize, the one every young physicist was learning as settled truth. To look at it and feel embarrassed by it, to think that nature would not actually fill all of space with an infinite invisible fluid just to make an equation behave, required a kind of confidence that bordered on arrogance, or a kind of taste that bordered on the religious. Majorana had both. He believed, the way Dirac believed, that the right description of nature would be clean, and that ugliness in a theory was a symptom of a mistake not yet found. Everyone else had decided the prediction was so spectacular that the ugliness underneath it did not matter. Majorana could not let it go. He kept that objection quietly for years. We will come back to it, because the day he finally acted on it, is the day this story splits open. But I am getting ahead of the man. Because before Majorana ever touched the question of antimatter, he established, in front of the most demanding physicist in Italy, that he was operating on a different level than everyone around him. And the way he did it tells you something about how this story ends. The first thing that happened, the thing every account of his life includes because it is the moment Fermi understood what had walked into his institute, involved a differential equation. Fermi was working on a model of the atom, the statistical model now called the Thomas Fermi model, and he had a nasty nonlinear equation to solve, the kind with no clean solution, the kind you grind out numerically. Fermi had spent about a week on it with a hand calculator, working through it digit by digit, and had produced a table of numbers. Majorana, skeptical, said almost nothing. He took the problem home. He recognized that it could be transformed into a different kind of equation entirely, and his recovered notebooks show he actually solved it two separate ways, using two original methods, neither of which Fermi had used. He came back the next day, walked up to Fermi, and asked to see his table of numbers. He compared Fermi's week of calculation to the slip of paper in his own hand. They matched, and Majorana, who had expected to catch an error, could not hide that he was impressed, which from him was almost unheard of. He took his degree under Fermi on the 6th of July, 1929, with a thesis on the quantum mechanics of radioactive nuclei. And he became part of the group that would become legendary, the Ragazzi di Via Panisperna, the Boys of Via Panisperna, named for the street where the institute stood. They gave each other nicknames that doubled as a hierarchy. Fermi was the Pope, because Fermi did not make mistakes. Corbino, the senator who funded everything, was the Eternal Father. And Majorana they called the Grand Inquisitor, because of the way he could take any idea, anyone's idea, including Fermi's, and dismantle it with a few quiet, surgical questions until there was nothing left. Bruno Pontecorvo, who was there, who later became a major physicist in his own right, described it plainly. He said that, not long after Majorana joined, the young man already understood physics deeply enough to argue with Fermi as an equal, and that Fermi himself considered Majorana the greatest theoretical physicist alive. Pontecorvo remembered Fermi's exact phrasing, and it is worth hearing, because it is the kind of thing Fermi never said about anyone. If a problem has already been posed, Fermi said, no one in the world can solve it better than Majorana. Sit with the weird cruelty hidden in that sentence. If a problem has already been posed. Because Majorana's tragedy, and the field's tragedy, was that he almost never bothered to pose the problems, or to publish the answers once he had them. In his entire life, he published 9 scientific papers. 9. A productive physicist of his caliber would publish that many in a couple of years. Majorana would solve something monumental, scribble it on a cigarette packet or the back of an envelope, work out that he was right, lose interest, and throw the packet away. The work existed only long enough to satisfy his own curiosity, and then it was gone. He treated some of the deepest results in 20th century physics the way you would treat a crossword you finished on the train. I want to give you one example that has nothing to do with antimatter, because it shows you the size of what he was throwing away. In 1932, the same astonishing year, Majorana wrote a paper on a relativistic equation for particles with arbitrary spin, what is now called the Majorana equation for an infinite component field. It was so far ahead of its time that essentially nobody understood it. The mathematics he used would not be properly developed by other physicists for another 5 or 6 years, and the full significance of what he had done was not appreciated until decades later, when Eugene Wigner and a generation of Soviet mathematicians rediscovered the same structures and realized Majorana had been there first, alone, in the early 1930s, with no one around him able to follow. He wrote it, He published it because for once someone pushed him, and then the field simply was not ready, and it sank. He kept doing this. He kept arriving at places the rest of physics would not reach for half a century, planting a flag and walking away before anyone arrived to see the flag. And the institute he did this inside was, for a few years, the most exciting room in the world. The boys of Via Panisperna were not just theorists. They were about to change the century in the most literal way imaginable. The building had a garden with a fountain and a goldfish pond, and there is a story, possibly polished by time but told by the participants, that in October of 1934, the group made one of its central discoveries almost by accident. When they found that passing their radioactive sources through water or paraffin, slowing the neutrons down, made them dramatically more effective at making other elements radioactive. The slow neutron. They are said to have run experiments using the goldfish fountain in the courtyard as a source of water to slow the particles. That discovery, slow neutrons, is a direct ancestor of the nuclear reactor and the atomic bomb. Fermi would win the Nobel Prize for the work in 1938, the same year Majorana disappeared, and would use the trip to Stockholm to collect it as his escape route out of fascist Italy, never returning, going straight to America to build the first reactor under a football stadium in Chicago. The men in that garden were 10 years away from Los Alamos, and they mostly did not know it yet. Majorana, the one some of them thought was the most gifted of all, was the one who left first, and left the most completely. Segre, who knew him as well as anyone, and who wrote about him later with a kind of baffled tenderness, described a man who was generous with his genius, in private and incapable of the ordinary ambition that turns genius into a career. Majorana would help anyone with a problem, would casually solve in conversation things that others would build a reputation on, and then refuse to put his own name to almost any of it. There is a phrase that attaches to him in these accounts, attributed in spirit to Fermi, that Majorana had gifts greater than anyone else in the world, and lacked only one thing that ordinary men generally have, which was plain common sense. It is a devastating thing to say about someone, and it was said with love, and it turned out to be the most accurate prediction anyone made about how his life would end. Word reached Rome about experiments in Paris by Irene Joliot-Curie and her husband, in which beryllium, when hit with radiation, gave off something that could knock protons loose from paraffin. The Joliot-Curies thought they were seeing some strange form of high-energy light. Majorana read the report and, in an afternoon, in his head, understood that they were wrong, and that what they had actually produced was a neutral particle with roughly the mass of a proton. A neutral nucleon. He worked out that this was the missing piece that explained the structure of the atomic nucleus. He told the group, he said, more or less, that those idiots in Paris had found the neutral proton and had not even realized it. And then he did nothing. He did not write it up. He did not publish. Within weeks, James Chadwick, in England, announced the discovery of the neutron and in time won the Nobel Prize for it. Majorana had understood it first, and not by a little, he had it cold. With the theoretical interpretation, the experimentalists themselves had missed. And he let it go, because publishing struck him as somehow vulgar, a thing other people needed to do. There is a pattern starting here, and I want you to hold on to it, because it is going to repeat at a scale that stops being a quirk of personality and starts to feel like something else. The most gifted physicist of his generation kept making himself disappear from his own discoveries. He kept declining to be seen. He kept performing the impossible calculation privately, under the table, and then walking out as if nothing had happened. The neutron was the first time he did it with something the size of a Nobel Prize. It was not the last time he made himself vanish. It was a rehearsal, and I want to be honest that this was not simple modesty. Because modesty is a virtue, and this was something closer to a compulsion. A modest person is reluctant to claim credit. Majorana was reluctant to exist on the record at all. He did not merely decline to publish the neutron. He seemed almost offended by the idea that one should publish, that one should plant a flag, that one should convert understanding into reputation. He had understood the neutral nucleon, understood it more deeply than the people who would win the prize for it, and he treated that understanding as a private possession that lost its value the moment it was shown to anyone. There is a kind of person who needs the world to witness their achievement in order for it to feel real. Majorana was the precise opposite. The witnessing seems to have spoiled it for him, and if you carry that forward, if you let that trait grow for 6 more years, it stops looking like a personality quirk and starts looking like the early symptom of a man who would eventually decide that the cleanest thing he could do with a life of staggering visible promise was to remove it from view entirely. But the neutron episode did one important thing. It pushed him, for once, toward an actual published idea about how the nucleus holds together. And that idea is why his name first crossed an international border. Because the question underneath the neutron was enormous. If a nucleus is a tight ball of protons, all carrying positive charge, all furiously repelling each other, why does it not blow itself apart in an instant? What holds it together? Majorana proposed a specific mechanism, a force that acts by having protons and neutrons exchange their positions, a kind of swapping that binds them. We still call a version of it the Majorana exchange force. And that idea is what carried him, in early 1933, out of Italy and into the single most consequential and most disturbing period of his life. It carried him to Germany. It carried him to Werner Heisenberg. And to understand why Germany broke something in him, you have to understand that he did not go there as a tourist. He went there at the exact moment the country was being handed over to the people who would burn it down. And a part of him, which is the part of this story I refuse to sound smooth for you, liked what he saw. In January of 1933, Majorana left Italy on a research grant and travelled first to Leipzig, where Heisenberg held court, and later to Copenhagen, where Niels Bohr ran the most important physics institute in the world. He was 26. He had qualified to teach at the university level the previous November, and in Leipzig, something genuinely good happened to him, which makes everything else harder to look at. He and Heisenberg became real friends. Heisenberg, who was only a few years older and already one of the founders of quantum mechanics, recognized exactly what Majorana was, and he did the one thing Majorana's own family and friends could rarely do. He got Majorana to publish. The nuclear forces paper, The Exchange Force, came out in a German journal in 1933, and it is the only paper of his that received immediate, wide recognition during his lifetime. And it happened because Heisenberg, in Majorana's own words from a letter home, did what he called propaganda for it, talked it up, made people read it. You can hear, in Majorana's letters from this period, a man briefly coming alive. He wrote to his mother on the 22nd of January that he had spent a long conversation with Heisenberg, who he described as extraordinarily courteous and likable. A few weeks later he wrote that the atmosphere at the institute was very pleasant and that he had good relations with Heisenberg and Hund and everyone else. For a man who crawled under tables to avoid being watched, this is the closest thing to happiness in the entire record of his life. He went on from Leipzig to Copenhagen, to Niels Bohr's Institute, which was the spiritual capital of quantum mechanics, the place where the strange new physics had been argued into its modern shape. By every account, Majorana was less at ease there. Bohr's Institute ran on long, exhausting, collective argument, everyone talking at once, the famous Bohr method of grinding a problem down through endless conversation, and that was close to Majorana's idea of hell. He worked best alone, in silence, in a locked room, and a place built on talking was never going to fit him. But the Leipzig friendship with Heisenberg was real, and it is one of the few warm things in the story, and it makes what came next harder to hold. Heisenberg had given him something almost no one else managed to. He had made Majorana feel that being seen was survivable. And then Majorana went home and spent the rest of his life proving it was not. You can watch the warmth drain out of the letters as the year goes on. The early ones are alive. The later ones turn cold and abstract and political. And it is the political turn that I refuse to leave out, because it is the part the legend cannot survive. I have to stop here, because the romantic version of Majorana, the gentle, doomed genius who fled the world out of moral horror at the bomb, is the version that gets told, and it is not honest. Here is what is also in the letters. On the 31st of July, 1933, while he was abroad, Majorana joined the National Fascist Party, and his letters from Leipzig express open sympathy with what the Nazi regime was beginning to do, including the expulsion of Jewish academics from German universities. In one letter he wrote, coldly, that it was inconceivable for a country of 65 million to be guided by a minority of 600,000. He was talking about Jewish Germans. A month before he vanished for good, he wrote to his mother, with what reads like pleasure, that from his new room he would be able to see Hitler pass by. Many of his own colleagues, the people who admired him, who tried for the rest of their lives to find him, were Jewish. Seger was Jewish. Pontecorvo was Jewish. Fermi's wife was Jewish. And the racial laws that Italy passed in 1938, the same year Majorana disappeared, would drive Fermi himself permanently out of Italy. I am not telling you this to perform a judgment for you. I am telling you because the legend of Majorana depends on him being a kind of secular saint who saw the moral abyss of physics coming and stepped away from it, and the documents do not support that man. They support a more uncomfortable one, a staggering intellect and a narrow, cold political heart in the same skull at the same time. If you want the real version of this story, you have to carry both, and the people who tell it usually drop the second one. I will not. He came back to Italy in the autumn of 1933, and he came back wrong. Something had happened to his body and to his spirit. He had developed acute gastritis in Germany, which some attribute to nervous exhaustion, and from the beginning of 1934 he began to withdraw. His father died that May, and Majorana began the long, slow disappearance that preceded the final one. He stopped going to the institute. He started staying home, in his room, for days, for weeks. His sister Maria, who is one of the most reliable witnesses to this period, insisted that he never stopped work. He worked at home, for long hours, deep into the night, on problems nobody else saw. He grew his hair long. He grew a beard. He cut himself off from the friends who had pulled him into physics in the first place. For roughly 4 years, from 1933 to 1937, the most brilliant theorist in Italy published almost nothing and was seen by almost no one. Try to picture what that means in a working life. He was in his late 20s, the age when a theoretical physicist does his best and most aggressive work, the age when Einstein had his miracle year and Heisenberg invented matrix mechanics. Majorana spent those years behind a closed door. The friends who had crossed over from engineering with him, who had dragged him into Fermi's institute, watched him receive. Segre, Amaldi, the others, kept building careers, publishing, traveling, becoming the famous names they would become, and the one they had all privately considered the most gifted simply stopped appearing. He did not announce a crisis. He did not explain. He withdrew the way a tide withdraws, quietly and without drama, leaving the people who knew him standing on a beach wondering where the water had. His mother worried. His sister insisted he was working, and she was probably right, because the symmetric electron-positron paper was reportedly finished in this period, which means the door he was sitting behind had the most important result of his life behind it, and still he did not come out. Whatever was happening to him, it was not idleness. It was a man slowly converting himself from a public figure into a private one, dimming his own visibility year by year, as if practicing for a darkness he had already decided to walk into. This is the part of the biography where the temptation is to reach for a diagnosis, and I am not going to give you one, because I cannot, and because the people who knew him could not either. What we have are the surface. A man who had touched something real in Leipzig, the recognition he had always refused, came home and chose silence and isolation for 4 years. We know he was working. We have a letter to his uncle Quirino from January of 1936 in which he mentions he is working on quantum electrodynamics. We know he was alive and thinking. We just do not know what it cost him, or what he was circling alone in that room with the door shut, doing the impossible calculation privately, the way he had done since he was a child under the table. And then, in 1937, he opened the drawer. Because here is a detail that I find almost unbearable. The paper. The one that made him immortal. The equation for a particle that is its own antiparticle. It had reportedly been finished, sitting in a drawer, essentially complete, since around 1933. For 4 years he had the thing that would carry his name into the 22nd century, finished, in a drawer, and he did not publish it. Because he did not care to. The only reason it ever saw daylight is that a national competition opened in 1937 for 3 full professorships in theoretical physics, and his friends and Fermi pushed him hard to enter. And to enter he needed a recent publication. So he reached into the drawer, pulled out the thing he had been sitting on for 4 years, sent it to Il Nuovo Cimento, and changed physics. Almost by accident, as an administrative formality. Now I need to tell you what is actually in that paper, because everything, the man, the disappearance, the structure of reality, the reason you are alive, runs through it, and I am not going to hand you the simplified version, because the simplified version is exactly the kind of sanitized thing this whole channel exists to refuse. Remember Dirac. Remember the infinite, invisible ocean of electrons, the Dirac Sea, the clumsy crutch Majorana had hated for years. Remember that the entire framework of antimatter, the framework that won Dirac the Nobel Prize, was built on the idea that an antiparticle is a hole in that ocean. Majorana's paper, titled in Italian Teoria Simmetrica dell'elettrone e del positrone, the symmetric theory of the electron and positron, did something that sounds technical and is actually a quiet act of demolition. He found a way to rewrite Dirac's equation so that the infinite ocean was not needed at all. He did it by finding a special form of the equation, using a particular set of mathematical objects now called the Majorana representation, in which the equation could be written entirely in real numbers. Dirac's version was riddled with imaginary numbers, the square roots of negative quantities, which is part of why it produced those troublesome negative energy mirror solutions. Majorana found a representation in which the wave equation admitted purely real solutions. And a purely real solution has a staggering physical consequence. It describes a particle that is exactly identical to its own antiparticle. Let me say what that means in the plainest terms I can, without lying to you about the depth of it. In Dirac's world, an electron and a positron are 2 distinct objects that happen to be related. They are partners. They annihilate when they meet because they are opposites. In Majorana's world, for a particle that carries no electric charge, there is no part. The particle and its antiparticle are not 2 things that resemble each other. They are one single thing, looked at from 2 directions. There is no anti-version sitting somewhere else in the universe waiting to meet it. It already is its own anti-version. And so there is no need for an infinite sea, no need for negative energy holes, no need for the entire apparatus Dirac had dragged in. The paper's own conclusion states it almost gently. The meaning of the Dirac equations is somewhat modified, it says, and there is no longer any need to speak of negative energy states, nor to assume, for any neutral particle, the existence of antiparticles. You should feel the floor shift slightly when you read that, because Majorana had just written, in a peer-reviewed journal, that the great triumphant symmetry of physics, the rule that every particle has a mirror twin, did not have to be true. For neutral particles, it might simply not hold. The twin might not be a twin. The twin might be the thing itself. There is a way to see how radical this is in terms of sheer bookkeeping. A Dirac particle, a normal one like the electron, carries 4 independent pieces, 4 degrees, the electron spinning one way, the electron spinning the other way, the positron spinning one way, the positron spinning the other. 4 states. Because the particle and its antiparticle are genuinely separate objects, a Majorana particle has only 2. Spin one way, spin the other. And that is the entire inventory, because there is no separate antiparticle to half the furniture is gone, not because it was hidden, but because it was never there. Where Dirac saw 2 objects in a mirror, Majorana saw 1 object and an illusion of a second. And what makes it almost eerie, a point Frank Wilczek made decades later, is how elegant the construction is. Majorana took Dirac's own method, the trick of finding a deeper equation underneath the obvious, and he turned that method back onto Dirac's equation itself, and he distilled out of it something simpler and stranger than the thing he started with. He used Dirac to unmake Dirac. He found, sitting inside the most celebrated equation of the age, a quieter equation that needed no infinite ocean, no negative energy holes, no antimatter at all for the neutral case. He did not add anything. He removed something, and the removal was the discovery. And there is one more consequence buried in this, and it is the one that makes the whole thing matter for the cosmos, so hold on to it. A Dirac particle conserves a quantity called lepton number, a kind of accounting that keeps matter and antimatter balanced in every reaction. A Majorana particle does not. Because if a particle is its own antiparticle, then the line between making a particle and making an antiparticle blurs, and the accounting that depends on that line breaks down. A Majorana neutrino is, by its very nature, a particle that can violate the conservation of matter over antimatter. Remember that. It is going to be the hinge the entire universe swings on. He pointed at a specific particle in nature and said, that one might be its own antiparticle. He pointed at the neutrino. I want to come back to the people now, because I promised you the personal and the physical are the same thread, and here the thread pulls tight. The same year he published this, the 1937 competition for the 3 chairs went forward, and the field of candidates was absurd. Majorana, Giulio Rocca, Giancarlo Wick, Giovanni Gentile the Younger. Any one of them was a serious physicist. The judging committee was chaired by Fermi, and the committee did something that, as far as the records show, had essentially no precedent. They looked at Majorana, and they decided that ranking him against the others in a normal competition was inappropriate, almost insulting, like grading Newton on a curve with 3 graduate students. So instead of placing him in the competition at all, they recommended to the Minister of National Education that Majorana be appointed directly to a chair of theoretical physics at the University of Naples, outside the normal procedure, for what the official language called his great and well-deserved fame. The committee report praised the exchange forces as fundamental to understanding why the nucleus holds together, and it singled out the symmetric electron-positron theory, the very paper we are discussing, as a method for finally eliminating what it called the extremely artificial and unsatisfactory hypothesis of an infinite density of negative energy electrons. The Diracs, the committee, chaired by Fermi, called the Nobel-winning idea artificial and unsatisfactory, and praised Majorana for killing it. He took the chair at Naples in late 1937. He began lecturing on the 13th of January, 1938. His students, the few who could follow him, described lectures pitched far above their head, the work of a man speaking from an altitude they could not reach. He moved into a hotel in Naples. He had, on paper, finally arrived. The recognition he had refused his whole life had been forced on him by a committee that did not even dare to rank him. There are small details from those final weeks that read differently once you know how the story ends. He kept to himself, ate alone, walked alone. He had grown reluctant even to lecture in front of a room, and there is a sense in the accounts of a man performing a role that did not fit him, standing at the front of a class delivering physics at a level the students could not absorb, going back each night to a hotel room. One of those few students, Gilda Senatore, who could follow him, would still be talking about him more than half a century later because of what he did with her in a corridor on his last day, a thing she did not understand at the time and spent the rest of her life turning over. He had, in those weeks, every external marker of a successful man at the start of a brilliant career, a chair won without competition, a famous name, a future, and something in him had already decided. He had 10 weeks left. And this is where I have to slow down and walk you through the disappearance the way it actually happened, hour by hour, because the documented sequence is stranger than any of the theories built on top of it, and because every single detail is going to matter when we get to what the equation implies. I have read the timeline many times, and it does not get less unsettling. It gets more. On Friday, the 25th of March, 1938, Majorana did something in the corridor of the Naples Physics Institute that nobody understood until much later. He stopped a young student named Gilda Senatore, one of the few following his lectures, and he handed her a folder. Inside were papers, his lecture notes, scientific writing. He told her, more or less, take these, hold on to them, we will talk about it later, and he repeated that phrase as he walked away. We will talk about it later. They never spoke again. The folder eventually made its way to the Institute's director. That folder, handed to a student in a hallway, is one of the only physical things he left behind, and he gave it away like a man emptying his pockets before going somewhere he could not carry anything. That same day, sometime before the money mattered, he had withdrawn the contents of his bank account, months of salary, in cash, and he wrote a letter to Antonio Corelli, the director of the institute and a man he considered a friend. Then, around 10:30 at night, he boarded a steamer, the Città di Palermo, leaving Naples for Palermo, across the open water in the dark. The letter to Corelli is the first of the documents, and it reads exactly like a suicide note. I will paraphrase it closely and quote only the smallest fragments, because the words deserve precision. He wrote that he had made a decision that had become unavoidable. He insisted there was not a trace of selfishness in it, but said he understood the trouble his sudden disappearance would cause Corelli and the students, and he begged forgiveness, above all for betraying the trust and the friendship Corelli had shown him over the previous months. He asked to be remembered to the people at the institute he had come to value. And then the line that has frozen everyone who has ever read it. He wrote that he would keep a fond memory of them all, at least until 11 o'clock that night, and possibly later. At least until 11 o'clock that night. He was on a boat in the dark, in the open sea, telling the director he would remember him fondly until 11 o'clock. There is only one thing a sentence like that is supposed to mean. And then the story breaks in half, because the next day it reverses. On Saturday, the 26th of March, Majorana arrived in Palermo. He checked into the Grand Hotel Sole, and he sent Corelli a telegram, urgent, telling him not to be alarmed, that a letter was coming. Do not be alarmed, letter to follow. And then he wrote that second letter, the one that takes the suicide note and tears it. He wrote that he hoped the telegram and the first letter had reached Corelli together. And then, the line, the sea rejected me. He wrote that the sea had rejected him and that he would be coming back the next day, returning to his hotel in Naples, perhaps traveling on the same boat as the letter itself. He said he did still intend to give up his teaching. And then, the strangest sentence in the entire affair, a flash of something almost like dark humor from a man supposedly in the depths of despair. He told Corelli not to take him for an Ibsen heroine, because the situation was different, and that he was available for further details. Do not take me for an Ibsen girl. He is referencing a character from a Henrik Ibsen play, a theatrical suicide, and he is telling his director, do not put me in that category. This is not that. The case is different. A man who, the night before, had written that he would remember everyone fondly until 11 o'clock, is now making a literary joke about not being a melodramatic stage suicide. And then, he bought a ticket and boarded the boat back toward Naples. Hold the two letters next to each other, because the contradiction is the whole case in miniature. The first letter is a goodbye, weighted, final, a man settling accounts before the end. The second letter, written the next day, retracts it, jokes about it, promises a return, and then the man performing the retraction vanishes anyway. He gave us a death note, and then a note saying ignore the death note, and then he made the death note true by disappearing, except possibly he did not die at all, and simply used both letters as cover to walk out of his life. Read it one way, and it is suicide with a moment of hesitation. Read it the other way, and it is the most carefully staged exit in the history of science. A man laying down two contradictory stories so that no one could ever be sure which thread to pull. He was, remember, the person Fermi said could solve any problem better than anyone alive. If the problem he set himself in March of 1938 was how to disappear so completely that 88 years later the answer would still be contested, then he solved it the way he solved everything. Perfectly, privately, and without showing his work. He is believed to have shared a cabin on that return voyage with a professor from the University of Palermo named Strazzeri. And from that night, the night of the 26th of March, 1938, on a boat steaming back toward Naples across the water he said had rejected him, there is no further reliable trace of Ettore Majorana. Not one. He was 31 years old. Corelli, who received the telegram, then the suicide letter, then the reversal letter, in a confusing sequence over a couple of days, did not go to the police immediately. It was not until Thursday, the 31st of March, that the disappearance was reported to the chief of police in Naples. By then, any trail was nearly a week cold. The family refused flatly to accept that he was dead, and they never applied for a declaration of presumed death. They mounted their own search. They pulled every string the Majorana name could pull, and the name could pull a great many strings. Fermi himself wrote to the head of the Italian government, to Mussolini personally, asking that the search be intensified, because, Fermi argued, Majorana was simply too valuable to Italian science to lose. The philosopher and senator Giovanni Gentile, one of the most powerful intellectuals in the fascist establishment, and the father of Majorana's friend, Giovanni Gentile the Younger, lent his weight to the family's efforts. The search even brushed against the famous prefect Cesare Mori, the man who had broken the back of the Sicilian mafia for Mussolini, the so-called Iron Prefect. The full machinery of an authoritarian state, plus the most prestigious scientist in the country, plus one of its most powerful philosophers, plus a legendary investigator, all turned toward finding one thin, dark-haired man who had stepped off a boat. The mother had handbills printed. The family wrote to monasteries, because even then, within weeks, the religious seclusion idea was alive. And there are accounts that a Jesuit church in Naples and a monastery had been approached by a man matching his description in the days around the disappearance, asking to be admitted, and turned away. A reward of 30,000 lire was offered. A notice ran in a national magazine describing him. 31 years old, around 170 centimeters tall, lean, dark hair and eye, with a long scar on the back of one hand. Nothing, the state searched, and found nothing, and eventually gave up. And when it gave up, Fermi, who had compared this man to Galileo and Newton, said something that I think is the truest sentence anyone has ever spoken about Ettore Majorana. He said that Majorana was so intelligent that if he had decided to disappear and not be found, then no one was going to find. It was, Fermi implied, useless to keep looking. The Grand Inquisitor had posed himself as a problem, and the one rule Fermi had stated years earlier was that if Majorana posed the problem, no one could solve it better than Majorana. He had built his own disappearance, and he had built it the way he built everything, which is to say better than anyone else could. There was a note he is said to have left for his family, separate from the Corelli letters, and it carries a different tone, quieter, almost tender. He asked them not to wear black for him. If custom demanded some sign of mourning, he wrote, they could wear it, but for no more than 3 days. After that, he asked them to remember him in their hearts, and, if they could, to forgive him. Forgive me. For what? For dying. For not dying. For leaving. For something he had seen. The note does not say, and the not saying is the whole problem. So what happened to him? This is where, over 88 years, the theories have piled up, and I want to walk through them honestly, counting them, because the accumulation itself tells you something. There are, broadly, 5 of them, and they cannot all be true. And the unbearable thing is that the evidence genuinely supports more than one. The first theory is the simple one. Suicide, he threw himself into the sea on the first voyage, or the second. The first Corelli letter reads exactly like a goodbye, and the 11 o'clock line is hard to read any other way. His closest colleagues, Amaldi and Segre, the men who knew him, leaned toward this in the end, perhaps because it was the explanation that let them stop searching. But it does not fit the rest. It does not fit the telegram telling Corelli not to worry. It does not fit the second letter saying he was coming back. It does not fit the withdrawn money, because you do not need months of salary in cash to jump off a boat. It does not fit the Ibsen joke. A man planning to drown himself does not stop to make a wry literary reference about not being a stage heroine, and it does not fit his family, who knew him and who never for one day believed it. The second theory is the monastery. Majorana was a devout Catholic, and there is testimony, including from Antonino Sicily, a prominent physicist who directs a scientific center named after Majorana in Sicily, that a Sicilian bishop reported Majorana had come to him in something like a mystical crisis. There are accounts that he approached religious institutions around the time he vanished, asking to be taken in. The Carthusian monastery at Serra San Bruno in Calabria, a place of near total silence, comes up again and again. The idea is that he did not destroy himself. He withdrew, completely and permanently, into a silence so total that the man who crawled under tables as a child finally found the one place where no one would ever watch him again. The third theory is flight, across the ocean to South America. And this is the one that refuses to die, because it is the one with photographs. Serious scholars, including the physicist Erasmo Recami, who spent decades assembling Majorana's letters and documents into the definitive record, took seriously the testimony of people who claimed to have known or seen Majorana in Argentina in the years after the war. The picture that emerges is of a man who did not die at all, who used the cash and the planning and the genius for self-erasure to do the most difficult thing of all, which is to simply walk out of one life and into another, on another continent, under another name. The fourth theory is the saddest, the beggar. Reclusive sightings in Sicily, a strange figure and persistent, hard to verify claims that a man who might have been Majorana lived for years on the streets, in Rome, in Sicily, brilliant and broken and anonymous. These stories are mostly second-hand, often relayed by witnesses now long dead, and scholars treat them with caution. But they haunt the edges of the case, the image of one of the great minds of the century reduced to a man muttering equations on a street corner that no one would ever recognize. And the fifth theory is the grand one, the one Leonardo Sciascia turned into a famous book in 1975 called The Disappearance of Majorana. Sciascia was a Sicilian writer, one of Italy's most important, a man obsessed with the unsolved and the deliberately obscured, and he approached Majorana the way he approached a mafia killing, as a case where the official story was a cover for something the powerful did not want examined. Sciascia argued that Majorana had seen, earlier and more clearly than anyone, where nuclear physics was going, that a mind that understood the neutron and nuclear forces in 1932 could see, in the late 1930s, the shape of the weapon coming, and that Majorana, rather than become one of the fathers of that weapon, chose to remove himself from the world entirely, a kind of preemptive moral refusal, vanishing so that his genius could never be conscripted into the destruction of cities. Sciascia even reached back into the family history, to a 19th century murder trial in which a servant had been accused of killing a Majorana infant, and read it as a kind of inherited shadow hanging over Ettore. It is a beautiful thesis, and it is the source of almost everything the public thinks it knows about the man, and it made the physicists who had actually known him furious. Amaldi and Segre considered it fiction dressed as history, an invention, a novelist projecting a moral drama onto a colleague who had shown no sign of any such thing. The argument between Sciascia and the scientists was real and bitter, and it cut to something deeper than the facts of one disappearance. Sciascia ended one of his replies with a line that still lands like a slap, that the men of his generation and the young ones entering the universities were living more and more like dogs, and that they had science to thank for it, science above all. He was using a dead physicist as a weapon against physics itself. The scientists never forgave it. And here is the friction I cannot. The scientists were right that there is no contemporaneous document, none, in which Majorana expresses fear of nuclear weapons, and right that the man's actual politics, the fascist party card, the cold letters from Leipzig, are not the politics of a moral refuser. The bomb prophet Majorana is, most likely, a character Sciascia built out of a real man, the way a sculptor builds something out of stone, leaving most of the stone on the floor. And yet, decades later, the Italian state's own prosecutors, looking at the hardest evidence they could find, reached for Sciascia's explanation anyway, because nothing else made sense of a genius who walked away from everything at the moment he had won it. The novelist's invented motive became the official one. That should make you uneasy about the line between what we know and what we need to believe. 5 theories: suicide, monastery, South America, the streets, and the prophet who saw the bomb and fled. And here is the part the popular tellings rush past, the abdication of authority that sits at the center of this case. The institutions that should have resolved this could not. The fascist state, with all its police power and all of Fermi's prestige behind the request, searched and failed. The family, with all its wealth and connections, searched and failed. The greatest physicists in the world, who loved him, searched and failed. And the official position, for decades, was a shrug. A man vanished, and the people whose job it was to find people simply could not, and eventually stopped trying. That should bother you. It bothered me, because it means that for most of a century, the answer to what happened to the most gifted physicist of his generation was, officially, we do not know, and we have given up asking. There is one more document I have to put in front of you before we go on, because it sits in the middle of all of this like a key nobody can find the lock for. In 1942, 4 years after he vanished, his friend Giovanni Gentile the Younger published an essay Majorana had left behind. It was not about physics, it was about the social sciences, and it carried the title, The Value of Statistical Laws in Physics and the Social Sciences. And its argument, written by a man who would later make his own future impossible to predict, is that the new quantum physics had destroyed the old idea of a determined, predictable world. In the old physics, if you knew the present perfectly, you could calculate the future with certainty. Majorana argued that quantum mechanics had killed that forever, that at the deepest level individual events are genuinely, irreducibly unpredictable, and that this was not a limit of our knowledge, but a feature of reality itself. And then he extended it, carefully, to human affairs, to society, to the behavior of people. He was arguing, in effect, that the future is not written, that a single trajectory cannot be forecast from the present, no matter how much you know. A man who believed the future was fundamentally unpredictable, who wrote down an argument that you cannot calculate where a single thing will end up, then made himself the unforecastable event. He turned his own life into a demonstration of his thesis. You cannot predict where he went. The essay says so. He made sure of it, until the file reopened. And when it reopened, in our lifetime, it reopened in 2 completely separate places at once, in a way that I do not think anyone has properly put side by side. It reopened in a courtroom in Rome, and it reopened in the deepest physics laboratories on Earth. The man and the particle came back at the same time, and I want to take them together, because I think they are the same return. Consider the timing, because it is almost too neat. The phone call to the Italian television program that reopened the human case came in 2008. Frank Wilczek's essay, declaring that Majorana the physicist had returned to the center of the field, was published in 2009. Within a single year, at the end of the first decade of this century, both Majoranas came back from the dead at once. A retired mechanic in Venezuela picked up a phone, and a Nobel laureate picked up a pen, and neither of them knew about the other, and they were describing the same resurrection. For 70 years the man had been a sad footnote in the history of Italian physics, and the particle had been a clever footnote in the theory of the electron, and then in the same breath of history. Both footnotes stood up and walked to the front of the room. I do not believe in omens. I believe in coincidences that mean nothing and only feel like they mean something. But I have turned this one over many times, and it refuses to flatten out. The man and the idea spent the same 70 years buried, and they came back in the same year, and they came back carrying the same property: the refusal to be pinned down, the talent for being present and absent at once. So let me take them together, because pulling them apart feels like a lie about the shape of the thing. Start with the man, because it is the stranger story and almost nobody knows it. In 2008, a television program in Italy called Chi l'ha visto, which means Who Has Seen Him, a long-running show about missing people, received a phone call. The caller was an Italian emigrant named Francesco Fasani, a mechanic who had been living in Valencia, in Venezuela. And Fasani said something extraordinary. He said that in the 1950s, In Venezuela, he had known a reserved, cultured, clearly brilliant European man who went by the name Bini. He described him as carrying himself like a prince. Fasani said he later came to understand, through another emigrant, an Argentine he called Carlo, that this Mr. Bini was none other than Ettore Majorana, the famous vanished Italian physicist, and that the two of them, Bini and Carlo, had originally met in Argentina before turning up in Venezuela. And Fasani had a photograph, taken in 1955 in Valencia, in front of a currency exchange. It showed Fasani standing next to this Mr. Bini. The photograph existed at all, only because Bini, who otherwise refused to be photographed, had needed an urgent loan, and the picture was taken in exchange for it. Fasani had kept it. On the back, someone had later written Bini Majorana, and the date, the 12th of June, 1955. And Fasani described one more thing, a detail almost too perfect, that has made some scholars suspicious for exactly that reason. He said that in Bini's car, an old yellow Studebaker, always cluttered with notes and papers, like the desk of a man who never stopped working, he had once found a postcard from the 1920s written by the physicist Enrico Majorana, Ettore's uncle, to an American, discussing the experimental nature of gravity. The Rome prosecutor's office opened an inquiry in 2011. They handed the photograph to the Scientific Investigations Unit of the Carabinieri, the RIS, who do forensic image analysis. And the RIS reported that when they compared the face of Mr. Bini in the 1955 photograph to images of Majorana, and crucially to images of Majorana's own father Fabio at the same age, around 50, they found 10 points of correspondence: the forehead, the nose, the cheekbones, the chin. They reported that even the angle of the ears matched. The features, they said, overlapped, and so, on the 4th of February 2015, the Rome prosecutor's office, through Deputy Prosecutor Pierfilippo Laviani, closed the investigation with a formal conclusion. They stated that Ettore Majorana had been alive in Valencia, Venezuela, between 1955 and 1959, living under the name Bini. They found no crime. They concluded that this appearance had been a voluntary choice, a man who walked away. And the prosecutors offered a motive, and the motive is Ciasia's thesis, wearing an official seal. They suggested the most likely explanation was that Majorana, frightened by what he had understood about the atom, had chosen to disappear. The Italian state, in 2015, officially declared that the man who vanished in 1938 did not die in 1938. Now, I told you I would be honest about what is solid and what is not, and here is where I have to be. This conclusion is contested, and the people contesting it are not cranks. Erasmo Recami, who knew the documents better than anyone alive, found the photograph and the postcard far from convincing as proof of Venezuela specifically, even as he accepted that the broader facts, the withdrawn cash, the planning, do suggest a man who intended to escape rather than die. There are real problems. The orderly, unworldly Majorana could not even drive a car, which makes the cluttered Studebaker strange. His relationship with his uncle Quirino had been difficult, which makes the carefully preserved postcard from that uncle of all people a peculiar thing to be carrying around South America 2 decades later. A facial comparison, 10 points of similarity, is suggestive, not conclusive, especially across a 20-year gap and against a relative rather than the man himself. And the case is exactly the kind that attracts people who want it to be true. A descendant of the family, Marcello Majorana, recalled cranks calling over the years to report Ettore in the mountains of Alaska or in the company of aliens. So the file is officially closed and genuinely open at the same time. The state says, the scholars say maybe, the evidence is thin, we cannot be sure. Which is to say, after 88 years and a state investigation, the honest position on what happened to Ettore Majorana is the same position Fermi held in 1938. He decided to disappear, and he was good enough to do it, and we do not know where he went. But the man was only one of the two things that came back. Because while prosecutors in Rome were staring at a photograph of a stranger in a Venezuelan currency exchange, physicists in laboratories buried under mountains were chasing the other half of him, the particle. And the particle's return is the part that should change how you think about your own body. For 70 years after 1937, the Majorana paper, in the words of the Nobel laureate Frank Wilczek, close to a footnote, a clever, elegant reworking of Dirac's equation that most physicists filed away as a curiosity. The particle that is its own antiparticle was a mathematical possibility nobody could find in nature. And then, slowly, and then all at once, it became one of the most important open questions in all of physics. And Wilczek wrote a piece in the journal Nature Physics in 2009 with a title that says everything. Majorana Returns. Wilczek described how Fermi had to push Majorana to publish the idea in the first place, how it stayed obscure for 70 years, and how suddenly, in his words, the concept seemed to be everywhere. He wrote that Majorana's central idea, which had long looked peripheral, had moved to the core of theoretical physics, and that it would be both disappointing and surprising if real Majorana particles, now being hunted, did not soon show up. Now being hunted. By whom, and how, and what would it mean if they found one? This is the heart of it, and I am going to walk you through the experiment in detail, because the detail is the content, and because what is being attempted in these underground laboratories is one of the most patient and audacious things our species has ever tried to do. Go back to the neutrino, the thing Majorana pointed at in 1937 and said that one might be its own antiparticle. And here is something worth sitting with. When Majorana pointed at the neutrino in 1937, no human being had ever detected. Nobody knew for certain it existed. The neutrino was, at that moment, a piece of desperate accounting. It had been invented, on paper, only 7 years earlier, by Wolfgang Pauli, and Pauli was so embarrassed by it that he did not publish it in a paper. He proposed it in a letter. In 1930, certain radioactive decays appeared to be losing energy that simply vanished, energy that went into the reaction and did not come out, which would mean the most sacred law in physics, the conservation of energy, was being broken. Rather than accept that, Pauli proposed that an invisible, nearly massless, electrically neutral particle was carrying the missing energy away, undetected. He wrote to a group of physicists, addressing them as dear radioactive ladies and gentlemen, and proposed his ghost particle as, in his own words, a desperate remedy. And then he confessed the thing that haunts every theorist. He said he had done a terrible thing. He had postulated a particle that could not be detected. He thought he had cheated. He thought he had invented something to balance the books that could never be checked, which is the cardinal sin of physics. Fermi, Majorana's own teacher, is the one who gave it its name. Pauli's particle needed a label, and since it was a tiny neutral thing, Fermi called it the neutrino, the little neutral one, in Italian. And in 1934, Fermi built an entire theory of radioactive beta decay around it, a beautiful, correct, foundational theory. He submitted it to the journal Nature, the most prestigious journal in science. Nature rejected it. They told him it was too speculative, too remote from physical reality to interest the reader. The editors of the most important scientific journal in the world looked at one of the foundational papers of 20th century physics and decided it was not worth printing. This is the pattern that runs through the entire history of this subject. The deepest ideas keep arriving before the institutions are ready to receive them, and the institutions keep saying no. Fermi published it in Italian and German instead, and it became one of the most cited papers in the history of physics, and Nature spent the next few decades living that one down. Pauli's terrible particle, the one he was sure could never be detected, was finally caught in 1956, 26 years after he proposed it, and 18 years after Majorana vanished. Two physicists, Clyde Cowan and Frederick Reyners, set up a detector next to a nuclear reactor in South Carolina, a reactor pouring out neutrinos by the trillions, and they finally registered the almost impossible interaction. They sent Pauli a telegram telling him his particle had been found. Pauli was alive to receive it. The ghost was real. The desperate remedy was a genuine piece of the universe. The neutrino is the most elusive particle we know about. It barely interacts with anything. Right now, as you read this, somewhere on the order of 100 trillion neutrinos from the sun are passing through your body every second, and almost none of them touch a single atom. They go through you, through the Earth, through the planet, and out the other side, as if you and the Earth were not there. They are nearly massless. They are electrically neutral. And that neutrality is the key, because Majorana's particle had to be neutral. A charged particle can never be its own antiparticle, because the antiparticle has the opposite charge, and a thing cannot be both positive and negative. But a neutral particle has no charge to flip, which means a neutral particle is allowed, by the mathematics, to be its own opposite. The neutrino is the only fundamental matter particle we know of that is electrically neutral. It is the one candidate in all of nature for being a Majorana particle. Majorana saw that in 1937, before anyone had even detected a neutrino at all. The neutrino was not experimentally confirmed to exist until 1956. He named the candidate before the candidate was known to be real. For a long time, it looked as if the question might be unanswerable for a boring reason. Through most of the 20th century, physicists assumed the neutrino had exactly zero mass. It was treated as a massless particle, like the photon. And a truly massless neutrino is a degenerate case where the difference between the Dirac kind and the Majorana kind becomes physically invisible. If that had held, Majorana's question would have been permanently undecidable, a distinction with no measurable consequence. But it did not hold. Starting in the late 1990s, two enormous experiments, Super Kamiokande in Japan and the Sudbury Neutrino Observatory in a mine in Canada, found that neutrinos do something impossible for a massless particle. They change. A neutrino of one type, traveling through space, oscillates into a neutrino of another type and back, as if it cannot decide what it is. This phenomenon, neutrino oscillation, is only possible if neutrinos have mass. Small, but not zero. The discovery won the Nobel Prize in 2015, awarded to Takaaki Kajita and Arthur MacDonald, and it did something more important than win a prize. It resurrected Majorana's question from the dead. Because once the neutrino has mass, the difference between a Dirac neutrino and a Majorana neutrino becomes real again, becomes physical, becomes something you can, in principle, measure. The question went from undecidable to merely brutally difficult. And the mass itself is a clue, and the clue points toward Majorana. The neutrino is not just light, it is absurdly, suspiciously light. It is at least hundreds of thousands of times lighter than the electron, which is itself the lightest ordinary matter particle. Nobody could explain why it should be so close to zero without quite reaching it, until theorists noticed that there is a natural explanation, and the natural explanation requires the neutrino to be a Majorana particle. It is called the seesaw mechanism. If there exists a very heavy, undiscovered partner to the neutrino, a heavy Majorana particle, then the mathematics forces the ordinary neutrino we know to be extremely light, in inverse proportion. The heavier the hidden partner, the lighter the visible neutrino. Like a seesaw, one end goes up because the other end goes down. And this elegant explanation for why the neutrino is so impossibly light only works if the neutrino is Majorana, if it is its own antiparticle. So the very lightness of the thing passing through your body by the trillions is itself a quiet argument that Majorana was right. Not an argument, a hint written into the mass of the most common particle in the universe. So is the neutrino its own antiparticle, or not? This is not a small question. It is, in a real sense, a question about whether the deepest layer of matter respects the difference between matter and antimatter at all. And there are two possibilities, and physics has names for them, and the names are the man's own name and Dirac's. If the neutrino is a normal particle, distinct from its antiparticle, the way the electron is distinct from the positron, we call it a Dirac neutrino. If the neutrino is its own antiparticle, identical to the antineutrino, we call it a Majorana neutrino. And here is the thing that should unsettle you. After all this time, with everything we know, we still do not know which one is the most common matter particle in the universe, and we cannot tell you whether it has an opposite. But we know how to find out. And this is where it becomes one of the most beautiful experiments ever designed, because nature gave us a single, specific, almost impossibly rare event that can only happen if the neutrino is a Majorana particle. And physicists have spent decades learning to watch for it. It is called Neutrinoless double beta decay. Stay with me, because this is the center of everything. There are certain atomic nuclei that are unstable in a very particular way. They cannot decay by emitting a single electron, the ordinary kind of radioactivity, for energetic reasons, but they can, very rarely, decay by emitting two electrons at once, in a single coordinate with two neutrons inside the nucleus, turning into two protons simultaneously. This is ordinary double beta decay, and it is real, and it has been observed. It is one of the rarest processes ever measured. And in the ordinary version, that decay also spits out two antineutrinos, one for each electron, to balance the books, because of a conservation law called lepton number that the universe normally obeys. Now here is the impossible version. Imagine the same decay, two neutrons becoming two protons, two electrons flying out, but with no neutrinos emitted at all. None. Neutrinoless. How could that happen? It can only happen if the antineutrino emitted by the first decay is the same thing as the neutrino needed to drive the second decay. If the neutrino is its own antipart, then the particle emitted by one half of the reaction can be immediately reabsorbed by the other half, internally, before it ever leaves the nucleus. The two would be neutrinos, meet inside the nucleus, and cancel, because they are the same thing meeting itself. And you are left with just two electrons and no neutrinos. The books do not balance. Lepton number is violated by 2 units, a conservation law that the universe appears to obey everywhere else is broken. If we ever see that, a double beta decay with no neutrinos coming out, it proves two things at once, instantly, with no ambiguity. It proves that lepton number is not truly conserved, and it proves that the neutrino is a Majorana particle, that it is its own antiparticle, that Majorana was right in 1937. One observed event would settle a question that has been open for almost 90 years. It would mean that the deepest matter in your body is a thing that is its own opposite, and there is a clean way to see it, in principle, which is what makes the hunt possible at all. In ordinary double beta decay, the two electrons that come out do not carry all the energy of the reaction, because the two neutrinos sneak away with a share of it, invisibly. So when you add up the energy of just the two electrons across many decays, you get a smeared out spread of values, because the neutrinos are stealing different amounts each time. But in the neutrinoless version, with no neutrinos escaping, the two electrons must carry every last bit of the energy, always the same total, every single time. which means the signal you are hunting for is a single sharp spike, a razor-thin line at one exact energy, sitting on top of the broad smear of the ordinary decays. Find that spike, that one precise line where the electrons carry all the energy and nothing escapes, and you have found the impossible event. The entire architecture, the mountains of shielding, the ultra-pure crystals, the near absolute zero cold. All of it exists to make the detectors precise enough to see whether that one thin line is there or not. So we look, and the looking is staggering, because this decay, if it happens at all, is the rarest thing anyone has ever tried to measure. We are not talking about a process that takes a few years, or a few thousand years. The experiments that hunt for neutrinoless double beta decay are setting lower limits on its half-life, the time for half the atoms to decay, that are almost impossible to hold in your mind. The strongest current limit, from an experiment called Camland Zen, operating deep under a mountain in Japan, using a tank of liquid loaded with the isotope xenon 136, has pushed the half-life past 3.8 times 10 to the 26th years. I need you to feel that number, because the framework I am working from is right that an unfelt number is wasted. The universe is about 13.8 billion years old. That is roughly 1.4 times 10 to the 10th years. The half-life limit these experiments have set is around 10 to the 26th years. That is not 1,000 times the age of the universe. It is not 1,000,000 times. It is more than 10,000 trillion times the current age of the universe. If you took a single one of these xenon atoms and asked when it would undergo this decay, the honest answer is that you would, on average, wait through the entire lifetime of the cosmos so many times over that the number stops meaning anything. And yet physicists hunt for it, because they are not watching one atom. They are watching unimaginable numbers of atoms at once, for years, in silence, hoping that out of all those trillions upon trillions, just a handful will do the impossible thing while the detector is looking. And the conditions required to look are their own kind of obsession, and they are worth describing, because they tell you how badly these people want this answer. The signal is so faint, so rare, that any ordinary radioactivity would drown it instantly. So the experiments are buried, deep, under thousands of feet of rock, to block the cosmic rays that constantly rain down on the surface. They are built from the most radioactively pure materials ever manufactured. Copper and lead, refined to remove nearly every trace of natural contamination, because a single stray decay from an impurity in the shielding could masquerade as the event they are hunting. The detectors are cooled too, within a fraction of a degree of absolute zero. They sit in the dark, under the mountains, for years, counting, let me name them, because they deserve it, and because the people in this field named one of the central experiments after the man himself. There is Gerda, in the Gran Sasso laboratory under the mountains of central Italy, which used germanium-76 and set a half-life limit beyond 1.8 times 10 to the 26th years before it finished. There is the Majorana demonstrator in a former gold mine in South Dakota, also using germanium, which reached beyond 8 times 10 to the 25th years. There is Core, also at Gran Sasso, using tellurium, an array of crystals cooled to one of the coldest cubic meters in the known universe. There is Camland Zen in Japan, with the current world-leading limit. And the two great germanium teams, Gerda and the Majorana demonstrator, have now merged into a single international collaboration of hundreds of scientists called Legend, which began taking data in 2023 and whose ultimate version is being designed to either find this decay or push its absence to beyond 10 to the 28th years, deep enough to test the most likely theoretical predictions for where the answer should lie. I want to pause on the people doing this, because it is easy to say hundreds of scientists and move on, and that phrase hides something worth feeling. There are physicists who have given their entire working lives to this one question and will retire without an answer. You build a detector that takes a decade to design and construct. You bury it under a mountain. You purify the materials for years. You cool it, you shield it, you switch it on, and then you wait, in the dark, counting, for years more, for an event that may never come even once, an event so rare that the universe itself has not existed long enough for a single one of your atoms to be likely to do it. You may spend 30 years watching for a thing you will never see, and the not seeing is itself the result, a slightly emptier spectrum, handed to the next generation who will build a bigger detector and watch a little longer. It is one of the most patient and least glamorous undertakings in all of science, and it is being carried out, right now, under mountains in Italy and Japan, and a gold mine in South Dakota, by people who have made peace with the possibility that the answer will arrive after they are gone, or will not arrive at all. They are waiting for a particle to meet itself. The same particle a man named after himself by accident in 1937, before he went to do the same thing. Decades of work, hundreds of physicists, buildings full of the purest matter on Earth, buried under mountains, refrigerated to near absolute zero, watching trillions of atoms in total darkness for years, waiting for a single particle to meet itself and vanish. And once, somebody said they had found it. This is the part of the modern story that almost nobody outside the field knows, and it is the cleanest example of the pattern this whole subject keeps repeating. Hans Volker Klapdor-Kleingrothaus was a respected German physicist who had run one of the earlier germanium experiments, the Heidelberg-Moscow experiment, the direct ancestor of Goethe, in the same Gran Sasso laboratory under the same Italian mountains. And around the turn of the millennium, in 2001 and then more forcefully in 2004 and 2006, he announced that he and a small group had seen it. The line, the spike, the neutrinoless decay. He claimed a detection, which would have meant the neutrino was a Majorana particle, which would have been one of the most important results in the history of physics, worth a Nobel Prize without question. And the field did not celebrate. The field recoiled. The claim was met with deep skepticism, even hostility. Other physicists argued the supposed signal was a statistical artifact, that the data analysis was unconvincing, that the peak he saw was buried in noise and other spurious lines and was not real. The dispute was bitter and personal, and the entire next generation of experiments, Goethe above all, was built, in part, specifically to test Klapdor-Kleingrothaus, to either confirm his claim or kill it. Goethe used the same element, germanium-76, in the same laboratory and watched, with far better technology, exactly the energy where he said the line should be, and it found nothing. Goethe saw a clean, empty spectrum where the claimed signal should have been, and it ruled the claim out. The man went to his grave with a detection almost no one accepted. The particle had slipped away again, the instant someone reached for it. First, it was a desperate ghost nobody could detect. Then it was claimed to be its own opposite, and the claim dissolved under scrutiny, and the question reopened, exactly as it had every time before. Decades of work, hundreds of physicists, and so far the result is silence. Not a single confirmed event the community accepts. The decay has never been convincingly seen, which means either the neutrino is a Dirac particle and Majorana was wrong about this, or the neutrino is a Majorana particle, and the decay is simply so rare that we have not yet watched long enough or with enough material. We do not know. After 88 years, the most patient experiment in the history of science has returned, so far a result of we cannot tell yet. I want to stop here and make sure the weight of this lands properly, because there is a pattern in it that connects directly back to the man. Majorana made himself impossible to find. He performed the operation of self-erasure so perfectly that the state, the family, and the greatest scientists of the age searched and came up with nothing. And 88 years later, the official conclusion is a contested photograph and a question mark. And the particle he predicted is doing the exact same thing. It is refusing to be found. It is either not there, or it is hiding inside a process so rare that watching the entire visible universe for its whole lifetime might not be enough to catch it once. The man and the particle share a single talent. They both know how to not be seen. And I will be honest with you, because the framework I trust demands it. I do not know how to think about that symmetry. I have gone back and forth on whether it means anything or whether I am pattern matching a coincidence into a story. A man predicts a thing that is its own opposite, a thing that can annihilate by meeting itself, and then he annihilates himself, and then, for 90 years, both of them refuse to be located. It is probably nothing. It is probably just the shape grief and mystery take when you hold them next to each other long enough, but I could not make it stop being there. There is a second front in the modern hunt, and it is messier, and it cuts straight to the abdication of authority, because it is a story about the people who should know being unable to tell you whether they have found it. Because the Majorana particle does not only haunt the neutrino, it also appears in a completely different form in the physics of materials, and that form has become entangled with one of the largest corporate bets in the history of technology. In certain exotic superconducting materials, theorists predicted that you could create something called a Majorana zero mode. It is not a fundamental particle. It is an emergent thing, a collective excitation at the ends of a tiny wire that behaves as if it were its own antiparticle. And these objects, if they are real and controllable, would be extraordinary, because they store quantum information in a way that is spread out and protected, making them in principle the ideal building block for a quantum computer that does not fall apart from the slightest disturbance. Microsoft bet its entire quantum computing program on them. This is not a small thing. This is one of the largest companies on Earth, wagering decades of research on building a machine out of Majorana's idea. And the history of that hunt is a cautionary tale about how badly we want things to be true. In 2012, a group in Delft, in the Netherlands, led by Leo Cohenhoven, reported the first tantalizing signature of a Majorana mode at the end of a nanowire. The field lit up. Then, in 2018, the same general group published a paper in Nature claiming a much cleaner, quantized signature, exactly the smoking gun the theory predicted. It was celebrated. And then it fell apart. Outside scientists raised concerns. A reanalysis showed that the cleanest data had been selected and the contrary data had been left out. In 2021, the paper was retracted. The authors issued an apology to the community for insufficient scientific rigor. A committee at the university found that the authors had selected data that supported the conclusion they wanted, though it found no evidence of deliberate fraud. One prominent physicist described the team as having been swept up in the excitement of the moment. The particle that is its own antiparticle had once again slipped away the instant someone claimed to have it. And it is still happening, right now, in our present. In February of 2025, Microsoft announced a chip it called Majorana 1, describing it as the world's first quantum processor built on what it called a topological core, using a new class of material. The announcement was enormous, and the scientific reception was, to put it carefully, divided. The paper published alongside the announcement, in Nature, demonstrated a specific measurement technique, and the editors of the journal attached a note clarifying that the results did not, on their own, constitute evidence of the topological states being claimed. At a major physics conference in March of 2025, a Microsoft scientist presented further data to a packed and largely skeptical room. Critics were blunt. One physicist, Henry Legg, at the University of St. Andrews, said publicly that any company claiming a topological qubit in 2025 was, in his words, selling a fairy tale, and warned that it undermined public confidence in the science. He said it did not look like Majorana particles, at least not to him. Microsoft stood behind its results. I am not here to tell you Microsoft is wrong. I genuinely do not know. And neither, as of now, does the field, which is the entire point. Look at what we have. The single most important question is the neutrino its own antiparticle, has been open for 88 years and the experiments return silence. The condensed matter version has produced one major retracted paper and one current claim the community largely refuses to accept. The people who should be able to tell you whether Majorana's particle exists are standing in front of their colleagues, presenting their best evidence and being told by serious scientists that it looks like a fairy tale. There is no authority you can appeal to here. There is no textbook that can give you the answer, because the answer is not known. The most basic question about the matter you are made of, whether at its root it is its own opposite, has no settled answer. And the people whose entire careers are devoted to it cannot agree on whether anyone has even glimpsed it. And it is worth being clear about what is at stake, because this is not a small piece of bookkeeping that physicists are arguing over out of habit. If someone finds that thin line of light under the mountain tomorrow, if Neutrinoless double beta decay is confirmed, it would be one of the largest results in the history of physics. It would be a Nobel Prize the morning it was verified. It would prove that the conservation of lepton number, a rule woven into the standard model, is not a real law of nature. It would confirm that the neutrino gets its mass through the seesaw mechanism, which means it would point, like a compass needle, toward a whole layer of physics beyond everything we currently know, a layer of heavy particles at energies we cannot reach in any collider we could build. It would turn leptogenesis from an elegant story into the leading established explanation for why the universe contains anything at all. A single observed decay would reach backward 13.8 billion years and forward into a theory of nature we do not yet possess. And it would do it by confirming a property a 31-year-old wrote down and stuffed in a drawer in 1933. That is what is sitting unresolved, not a footnote. The reason for existence, possibly, waiting on a measurement. And the institutions have been trying, with everything they have, for the better part of a century. Think about the sheer scale of the effort that has gone into this one question. Generations of physicists have given their careers to it. Hundreds of millions of dollars have gone into the mines and the crystals and the cold. Some of the most precise instruments humans have ever built exist for the sole purpose of answering whether one kind of decay happens. And the answer is still not in. The most expensive, most patient, most carefully shielded experiments in the field have produced, after all of it, the same two words Fermi used about the man. We do not know. There is something almost unbearable in that symmetry. We threw the full weight of 20th and 21st century science at both halves of Majorana, the man and the particle, and both halves have so far refused to be caught. That should make you feel something close to vertigo. And I want to push you the rest of the way over the edge now, because we have arrived at the implication. And the implication is the reason any of this matters beyond a sad biography and a difficult experiment. The implication is about why you exist at all. Here is a fact that once you understand it, is genuinely difficult to live with comfortably. According to our best theories of the early universe, matter and antimatter should have been created in exactly equal amounts in the first instant after the Big Bang, equal parts, and matter and antimatter, when they meet, annihilate completely into light. So, if the early universe made equal parts of each, they should have found each other, all of them, and annihilated all of them. And the universe today should contain no matter at all. It should be a thin, cold bath of light and nothing else. No galaxies, no stars, no planets, no carbon, no you. The default outcome of the laws of physics, applied to the beginning, is a universe made entirely of light with nothing in it to see the light. And yet, here you are. There is matter. There is a great deal of matter, an entire cosmos of it, and there is almost no antimatter anywhere. Something tipped the balance. Somewhere in the first fraction of a second, for every billion or so antimatter particles, there were 1,000,000,001 matter particles. The billion pairs annihilated, flooding the universe with light. And the leftover one, the residue of the imbalance, the rounding error, became everything. Every atom in every star, every molecule in every living thing, every neuron in your brain that is processing this sentence is built from that surplus. You are the rounding error. You are what was left over after the great annihilation, the single part in a billion that did not have a partner to destroy it. And the light from that annihilation did not go away. This is the part that gives me a kind of vertigo I cannot shake. When those billion pairs of matter and antimatter destroyed each other in the first instant, they turned into photons, into light. And that light is still here. It cooled as the universe expanded over 13.8 billion years, stretched out until it dropped below visible light, below infrared, down into microwave. And it now fills all of space as a faint glow we call the cosmic microwave background. It is the oldest light there is. And if you count, there are roughly 1 billion or 2 of those leftover photons for every single particle of matter in the universe. That ratio, about 1 billion to 1, is the fossil of the slaughter. It is the receipt. For every atom in your body, there are around 1 billion photons still drifting through the cosmos, the cremated remains of the antimatter that did not survive, and of the matter that died with it. You are not just the survivor of the annihilation. You are walking around inside its afterglow, bathed in the light of the near-total destruction that you, by 1 part in 1 billion, escaped. The static between channels on an old television, a small fraction of it, is that light. The death of almost everything, hissing quietly in the background of an empty channel, while the 1 in 1 billion that lived assembles itself into a creature that can notice. And the deepest question in this entire field is, what tipped the balance? Why was there 1 extra matter particle per billion? What broke the symmetry between matter and antimatter just enough to leave a residue? In 1967, the Soviet physicist Andrei Sakharov, the same man who designed the Soviet hydrogen bomb and then spent the rest of his life as a dissident fighting the regime that built it, worked out the conditions any explanation would have to satisfy. He laid down 3 requirements for a universe to start balanced and end up lopsided in favor of matter. The laws of physics have to allow the total amount of matter to change rather than stay fixed. They have to treat matter and antimatter slightly differently, a subtle asymmetry called CP violation. And the whole thing has to happen while the universe is out of equilibrium, which the violent expansion after the Big Bang guaranteed. 3 conditions. And the first of them, the requirement that the count of matter particles is not absolutely conserved, that the books are allowed to not balance, is precisely the thing a Majorana particle delivers. An ordinary Dirac neutrino keeps the books balanced forever. A Majorana neutrino, by being its own antiparticle, lets the count change. It is the one ingredient nature seems to need, and it is exactly the ingredient Majorana wrote down. And the leading candidate explanation, the one a great many physicists consider most natural, runs directly, precisely, unavoidably through the property Ettore Majorana wrote down in a drawer in 1933 and published as an administrative formality in 1937. The mechanism is called leptogenesis, and it works like this. If neutrinos are Majorana particles, if they are their own antiparticles, then very early in the universe, heavy relatives of the neutrino could decay in a way that does not produce matter and antimatter in equal amounts. Because the Majorana property allows lepton number to be violated, it allows a slight preference, a tiny asymmetry, to be generated. A small excess of matter over antimatter, manufactured in the first moments by particles that are their own opposites. That excess, processed through the physics of the early universe, becomes the 1 in a billion surplus, becomes the leftover, becomes the matter that survived, becomes everything. Picture it as carefully as the theory allows. In the first sliver of a second, the universe is full of these heavy Majorana particles, the heavy partners the seesaw requires. They are unstable, and they decay. And because they are their own antiparticles, and because of the subtle matter-antimatter asymmetry that Sakharov said must exist, they decay just slightly more often into matter than into antimatter. Not dramatically. A hair, a lean. For every so many decays into antimatter, a few more into matter. Run that across the unimaginable number of these particles filling the newborn cosmos, and the hair becomes the surplus, and the surplus, after all the annihilation is done, becomes the 1 part in a billion that is left standing. The lean of a decaying heavy cousin of the neutrino, 10 to the minus 30-something seconds after the beginning, is the reason there is a reader for this sentence. And the whole chain hangs on the first link, which is whether the neutrino is its own antiparticle. Knock out that link and the chain does not hold, and we are back to not knowing why anything is here, which is exactly where we still are. Do you understand what this means? If Majorana was right, if the neutrino is its own antiparticle, then the reason there is something rather than nothing, the reason the great annihilation left a residue instead of pure light, is the exact property he discovered. The thing that is its own opposite is the thing that allowed an imbalance, and the imbalance is the only reason any matter survived to become you. The man who wrote down the equation for a particle that is its own antiparticle may have written down the reason the universe is not empty. He may have identified the single property responsible for your existence. And then he took that property, the ability to meet your own opposite and annihilate, and he applied it to himself, and he vanished into something like light, and left no body, just a residue, a folder handed to a student, 2 contradictory letters, a photograph in a Venezuelan currency exchange 20 years later that may or may not be him. And here is the second foreshadow paying off, the thing I planted at the beginning. I told you the universe should have annihilated itself, and did not, and that the reason it did not might be the thing he wrote down. This is it. This is the thing. The survival of the universe and the property of self-annihilation are possibly the same property. The thing that lets matter meet its opposite and vanish is the same thing that, run in reverse in the early cosmos, let a little matter refuse to vanish. He found the door that swings both ways, annihilation and survival, the same hinge, and we still cannot confirm it. That is the part that I keep returning to and cannot resolve. The entire edifice, the reason you are made of something rather than nothing, the answer to why the cosmos is not an empty bath of light, may rest on whether the neutrino is a Majorana particle. And that single question is sitting right now, undecided, in a refrigerated chamber of ultra-pure copper buried under a mountain, being watched in the dark by people waiting for an event that may take longer than the universe has existed to happen even once. The answer to why you exist is down there, in the silence, refusing to declare itself. I want you to feel how close this is to you, because it is easy to file all of this under cosmology, under things that happened far away and long ago, and that is a way of keeping it, and it is not safe. The sun is fusing hydrogen in its core right now, and every one of those fusion reactions throws off neutrinos, and they take about 8 minutes to cross to the Earth, and then they pour through you. On the order of 100 trillion of them through your body every second, through the chair you are sitting in, through the bones of your hand, through the part of your brain holding this sentence. They do not stop because you are there. You are not solid to them. And the entire question of this script, the question Majorana opened in 1937, and that no experiment on Earth has closed, is whether those particles streaming through your tissue this second have an opposite somewhere, or whether each of them is its own opposite, alone, complete, needing nothing else to be cancelled, because it already contains its own cancellation. The thing that may be the reason you exist is also the thing passing through you in uncountable numbers in this exact moment, and it will not tell you what it is. The cosmic question and the bodily question are the same question. It is happening inside you while you wait for the answer, and the answer, when it comes, if it ever comes, will arrive the way Majorana arrived at everything. Quietly, late, and after the people waiting had nearly given up. A single thin line of light at one exact energy in a detector under a mountain after years of darkness. Or never. The experiments may run for decades more and see nothing, and the silence would not prove the neutrino is a Dirac particle. It would only prove the decay is rarer than we have yet managed to rule out. There may be no clean ending. There may only be a deeper and deeper inability to say, which is, when you think about it, exactly the shape of the other half of the story. The man, too, may have no clean ending. The file says Venezuela. The scholars say maybe. The honest answer, for the man and for the particle, is the one Fermi gave in 1938. He was good enough to disappear, and we cannot find him, and we may have to live with that. I want to come back to the man one final time, because the framework I write within insists, correctly, that the ending should return to the human being, and because there is nowhere else this can land. Think about what he actually did. A boy who hid under tables to do calculations no one could watch. A young man who understood the neutron and let the Nobel Prize go to someone else rather than be seen taking it. A physicist who found the deepest results of the century and threw them away on the backs of envelopes because being known was somehow unbearable to him. A man who wrote, in the symmetric theory of the electron and positron, that for a neutral thing, the distinction between a particle and its opposite might simply dissolve, that the two might be one thing seen from two sides. And then, a man who, weeks after finally being given the recognition he had spent his life refusing, withdrew his money, boarded a boat into the dark, wrote that he would remember everyone fondly until 11 o'clock that night, and then wrote that the sea had rejected him, and then was never reliably seen again. He spent his whole life rehearsing his own disappearance. The neutron was a rehearsal. The 4 silent years in the locked room were a rehearsal. He kept practicing the act of being identical to his own absence, of being present and gone at the same time, of being a thing and the negation of that thing in the same breath. And the one idea he could not throw away, the one he kept finished in a drawer for 4 years, the one that finally outlived him, was the idea of a particle that is its own opposite, a thing that does not have a separate enemy because it is its own enemy, a thing that can erase itself by meeting itself. He did not just predict the Majorana particle. He was the Majorana particle. He met his own opposite and annihilated, and what is left is a residue we cannot fully account for, an asymmetry, a story that does not balance, an official file that says he lived, and a scientific consensus that says we do not know, a photograph that may be him and may be a stranger, a particle that may be the reason for everything and may not exist at all. And you are sitting inside the same unresolved question, whether you knew it or not. Right now, 100 trillion neutrinos a second are passing through your body, through your eyes, through the thought you are having about this sentence. And we cannot tell you whether even one of them has an opposite, or whether each is, like the man who named them, a thing that is its own opposite, complete and alone, needing no partner to be destroyed, because it is already both. The matter you are made of is, at its root, an open question wearing the answer's clothes, the leftover of an annihilation that should have taken everything, the residue of an imbalance that the laws of physics, run forward from the beginning, say should never have survived. He found the door. He showed us that for the neutral things, the deepest things, the boundary between a thing and its negation might not exist. And then he walked through it, in the dark, off the coast of Sicily in March of 1938, and the Italian state spent the next 77 years failing to prove he had ever come out the other side. The equation is still on the page. The particle is still in the dark under the mountain, refusing to be either real or unreal. The man is still, officially, alive in a country he reached by methods nobody can reconstruct, under a name that was not his, in a photograph that may be a stranger. And the neutrinos are still passing through you, right now, in their trillions, carrying the answer to why you exist, and saying nothing.